Hey everybody, happy Monday. Let's pick up 2.1 and move forward with this. My goal for today is to finish the 2.1 note sheet. There's not a ton left to do. We got some things. We're going to talk about electronegativity. We're going to talk about the different types of bonds and the bonding spectrum in chemistry. And then we'll call it a day after we finish this 2.1 worksheet. Please be aware that my hope is that I have your tests done today. Monday, so I can get you those grades. My gradebook's a smidge behind. We had a lot of stuff kind of come in over the last week and a half, so I'm going to try to catch up and have everything up to date by the end of the day today. So please check Infinite Campus. If something doesn't look right, or if something is missing, send me an email, and we'll try to clear it out and make sure that we understand what we're missing and what we're not missing. Okay. Some people have tried to submit assignments and they haven't fully uploaded correctly, and I've sent some emails to try to, have you resend it to me or whatever the case may be. Just check your grades, check your stuff. If something's not there that should be there or something is missing that you definitely turned in, shoot me an email. Let's figure it out. Let's get to the bottom of it so I can fix that grade before we have progress grades come out, which are going to be actually pretty soon. So anyway, let's talk about 2.1. So in this note sheet, we are discussing... Sorry about that. In this note sheet, we are discussing the types of chemical bonds, and we're also, as a result of that, we're talking about something new called electronegativity. Electronegativity is how strongly an atom attracts shared electrons towards its nucleus. Okay, so you can think of it kind of like this. I have this nucleus, I have this nucleus, atom 1, atom 2, and between those two atoms, if there's a covalent bond, I have electrons. Each chemical bond is 2 electrons, okay? So if I have 2 electrons between these 2 atoms, they are not often shared equally, okay? The electrons in that bond aren't necessarily shared equally. One of those nuclei will most likely have a stronger attractive force towards those electrons that are being shared. As a result, the electrons are actually shared unequally. Now, the measure of how strongly an atom attracts these shared electrons towards its nucleus is called electronegativity. Higher electronegativity means stronger attractive force towards those shared electrons, and it leads to an uneven sharing or an uneven distribution of electrons in that chemical bond. Okay, so this was last week's stuff. Let's keep going. All right, we talked about the 5 most electronegative elements on the periodic table. Again, the general trend. Across a row from left to right, elements become more electronegative. And then up a column from bottom to top, elements become more electronegative. The 5 most electronegative elements on the periodic table are right here. Okay? These 5. And those are fluorine, oxygen, nitrogen, chlorine, and bromine. The mnemonic is phone, Chloe, bro, F-O-N, phone, C-L, Chloe, B-R, bro. Phone, Chloe, bro, F-O-N, C-L, B-R. The 5 most electronegative elements on the periodic table. It really helps to know these 5 because anytime you see any of them, you can understand that those are the elements that are going to be hogging the electrons, that are going to be pulling those shared electrons in chemical bonds towards those nuclei or towards that element. Okay, so this is kind of a nice little way to pick those out really, really quickly. All right, so let's look at an example. Okay, so I have a bond between carbon and fluorine. There's my carbon atom, C, my fluorine atom, F, and the dash between them is the bond. All right, so this right here, this chemical bond, okay, this holds or is 2 electrons. Okay. When atoms make bonds between them, it is 2 electrons in a single bond. Every bond between 2 atoms is 2 electrons. So, covalent bonds are made of 2 shared electrons between the atoms. Fluorine is very electronegative. Let's recap what the heck that means again, right? This element, fluorine, is the most electronegative element on the entirety of the periodic table. What that means is that these shared electrons are going to be pulled towards fluorine, okay? This bond and the 2 electrons in that bond are not equally distributed. Each of these atoms or each of these elements has a different electronegativity. The element that is more electronegative will pull the shared electrons in that direction. So this bond is actually shifted or pulled towards the fluorine just a little bit, okay? It hogs electrons. In fact, it hogs electrons better than any other atom. Since the electrons in this bond are pulled towards the fluorine atom, we will draw a partial negative charge by fluorine. This is new, okay? Last year, whenever we talked about charges, we usually were talking about ions, right? We have a negative fluoride. We have a positive sodium ion, 1 minus, 1 plus, right? Full magnitude of charge, 1 minus, 1 plus, 2 minus, 2 plus, 3 minus, 3 plus. That was always nice whole numbers. This year, we're going to introduce partial charges, okay? It's less than 1. So, fluorine, because it is more electronegative than carbon, means that these electrons are going to be pulled in that direction. Electrons have negative charge. As a result, we would expect that on this side or near the fluorine atom, we have a partial negative charge. That little music note looking thing is called delta. All right, it's a lowercase delta. And we put a negative sign. That lowercase delta represents partial, all right? Not a full 1 minus, less than 1 minus. But the end result is that there is some negative charge on that fluorine, all right? And you can see this in my sentence too, right? So the fluorine atom in this case doesn't have a full 1 minus charge like a fluoride ion would, but a smaller charge because the shared bonding electrons are pulled towards the fluorine, or it. So if fluorine gets a partial negative charge, then the carbon gets a partial positive charge. Okay, remember, this is a neutral compound, right? Anytime we make these compounds in chemistry, we make them neutral. The charges cancel out or balance out. So if fluorine is partially negative, the carbon on the other side must be partially positive. The electrons in this bond are pulled towards fluorine, partial negative. The electrons in this bond are pulled away from carbon, partial positive. The way you can tell which way the electrons are going to be pulled is all based off of electronegativity. This is more electronegative than that. Fluorine is more electronegative than carbon. And that's why we get the partial negative and the partial positive charge where they should be. Since both atoms end up with, I'll move my video for a second here. All right, we'll go right there. Since both atoms end up with partial charges, we call this a polar covalent bond. We will use lowercase Greek letter delta to show the partial charges. Polar. Okay. Have you ever heard the term polar opposite, right? Polar means two different competing things. In this case, polar in chemistry means you've got a positive spot, you've got a negative spot. That's what it's trying to imply. Okay? So the word polar, and more specifically polar covalent bond, means this is a bond that is shared, has shared electrons, but they are shared unequally, and that results in partial charges. All right. Draw a water molecule and include partial charges where appropriate. So let's draw a water molecule. We have H2O. That's the formula, right? Let's draw this out. Oxygen is in the middle. And on either side, we have a bond to a hydrogen. Okay, so there's my oxygen atom, hydrogen, hydrogen atom. These long dashes are my covalent bonds, where the electrons are being shared. Now, you might be asking yourself, hey, Mr. Brosnan, why didn't you draw that in a nice line? Why did you make it bent? Well, it is bent, actually. Not that we know that yet, okay? Eventually, we'll start talking about molecular geometry. And what I mean by that is the shape and the angles of molecules, okay? So we aren't there yet, but I can tell you that water is a bent molecule. And it'll make more sense when we eventually get to that topic. All right, but just hang with me for today. This is water. Now, the question is does water have partial charges? Or are these bonds shared equally? Remember, each bond is 2 electrons. And now let's look at these two elements right here. I have oxygen, I have hydrogen. which of those is more electronegative? Okay, well, you probably don't know offhand, right? But let's go back to the periodic table. As you go up and as you go to the right, electronegativity increases. The 5 most electronegative elements are the phone Chloe bros, FON, ClBr. Oxygen is one of the 5 most electronegative elements on the periodic table. Hydrogen is not. Okay, so if I remembered my mnemonic there, I would be good to go. I would recognize oxygen as very electronegative, and I would recognize hydrogen as not one of those. That was kind of lame. All right, so as a result, these shared electrons are being pulled towards the oxygen, and we get a partial negative charge by the oxygen. If these shared electrons are being pulled away from the hydrogen is going to get a partial positive charge. The same thing's going to happen on the other side, right? The exact same elements. I have oxygen, I have hydrogen. Oxygen's more electronegative, it's partial negative, and I'm just going to leave one of those symbols. I'm not going to draw a second symbol, okay? And the hydrogen, where these shared electrons are being pulled away from, is partially positive charge. Okay? That's all we're really doing. That's what you need to think about now. All right? We're going to be trying to identify these partial charges because they're going to help us answer more questions or later questions this year. All right? But it's all about electronegativity. Which is more electronegative? Oxygen. Awesome. That means these shared electrons are pulled in that direction and electrons are negatively charged. As a result, both of these bonds pulling towards the oxygen give us a partial negative around nearby the oxygen, and both of these shared bonds being pulled away from these 2 hydrogens make the 2 hydrogens partially positive charge. Now, I already talked about how partial charges aren't 1, right? They're less than 1. Now, I have no clue what that number actually is. Okay? This could be like 0.4, that could be like 0.4, this could be like 0.8. I don't know. It doesn't matter. What does matter is that you understand that when we write these partial charges, it's less than 1. We will never define what the numerical value actually is on these partial positive and partial negative regions. All right, we got some questions now. Well, not quite yet. I'm sorry, getting ahead of myself. So the bonding spectrum is organized by difference in electronegativities of atoms. Bonds become more polar when the difference between the electronegativities increases. Place the following bonds on the arrow according to their difference in electronegativity or their polarity. Okay, so I have a little chart. This little chart on the left-hand side over here, this is the numerical values of electronegativity. On It's Learning, I think I have posted an electronegativity periodic table, which has like the values for every single element. If you want to look at that, you're more than welcome to. But oftentimes I'll just provide you a little chart when we look at these types of problems. Okay, so here's the deal. We want to look at these 5 bonds and rank them from smallest difference in electronegativity to biggest difference in electronegativity. And as a result, we're then going to place them on my electronegativity spectrum. I'm going to move me way up to the top corner. Okay, so let's look at this. First bond I have is chlorine-chlorine. Well, if it's one element bonded to itself, there's no difference, right? None at all. Chlorine has an electronegativity value of 3.0, but so would the other chlorine. If this one has an electronegativity of 3, this one has an electronegativity of 3, it's the same. So which element's going to pull more strongly on those shared electrons between them? Neither, right? That makes sense. This is what we call nonpolar covalent, and I'll scroll down just a little bit. Okay? This is called a nonpolar covalent molecule, or a nonpolar covalent bond. And the reason why it's nonpolar is because there's no difference. All right? Remember, and I'll talk about this later as well on this slide, polar means that there are opposite ends. In other words, a positive region and a negative region. If there aren't those, because in this case we have no partial charges, we would call this nonpolar. It is this exact same value. Nonpolar covalent is what we would call this bond. It's a nonpolar covalent bond. Next, Carbon and nitrogen. Let's find carbon. Carbon has a value of 2.5. Nitrogen has a value of 3.0. Okay? As a result, because the nitrogen is a higher electronegativity, this would be partially negative charged, and this would be partially positive charged because of that difference. This, with a difference of 0.5, is going to be somewhere, I don't know, there-ish. Now, here's the deal. Polar covalent is classified as anything bigger than 0. All right? The difference between nitrogen and carbon in terms of electronegativity was 0.5. This is called a polar covalent bond. Even though it's not a big difference, there still is a difference, and it's more than 0, right? We do have a partial negative, we do have a partial positive. We call this polar covalent. The next one, francium and fluorine. Fluorine has an electronegativity of 4. Francium has an electronegativity of 0.7. The difference is 3.3. That is as large of a difference as you can possibly get. I have taken the upper right fluorine and the bottom left francium and made a bond between them. This is a huge, 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 huge difference between electronegativity. And as a result, this guy goes as far over to the right as we can possibly get. My slide is kind of screwed up here. I'm going to see if I can move this. There we go. I'm going to screw it. There we go. That's much better. I'll fix my arrows. So the francium and the fluorine, with a huge difference in electronegativity, give us what we would think of as, or what we know as, an ionic bond. Okay? So when you have a difference in electronegativity between two atoms that's over 2, we call this ionic. Essentially, here's what happens. Because fluorine's electronegativity is so much higher, this results in the electrons being fully transferred over to fluorine. They're no longer shared. And that's what an ionic bond is, right? A covalent bond is shared electrons. An ionic bond is when electrons completely transfer. Electrons transfer when the difference in electronegativity is really, really large. Essentially, this nucleus of fluorine pulls on these electrons so much more strongly that it just completely takes them. It steals them. It completely removes them from francium, and it's now going to make fluoride 1 negative and francium 1 plus. All right? So this is the difference between last year. Last year it was like, oh, you got a metal and a nonmetal. It's ionic. Okay, great. And that kind of works. It mostly works. But in reality, it's more nuanced. There's more gray area in terms of bonding and identifying what kind of bond you have. So this year, in order to identify the correct type of bond, we're going to use electronegativity sometimes. And we're going to give you these values. When I give you these values, what you're looking for is, what's the difference between the two atoms in my bond? If that difference is 0, it's nonpolar covalent. If that difference is bigger than 0, but less than 2, we would probably call that polar covalent, meaning that the electrons are still shared, but they're shared unequally, and we get partial charges as a result. Is the difference bigger than 2? If it is, now that's ionic. Now essentially the difference in those attractive forces is so large that the electrons just fully transfer. I hope you're hanging with me. I know I've kind of doubled back on the same exact concept like 4 times, but I want to make sure it kind of clicks, all right? Next, oxygen and chlorine. Oxygen, electronegativity is 3.5. I kind of wrote over it, but you can see it. And chlorine, electronegativity is 3.0. We have a difference. Oxygen is more electronegative than chlorine. This would give us a partial negative over here. This would give us a partial positive over here. And this is going to be a polar covalent bond. Exact same difference we had earlier, right? The difference between carbon and nitrogen was 0.5. The difference between oxygen and chlorine is 0.5. They would have the exact same difference, and they're both polar covalent. Still shared, the electrons are still shared. It's just that this is a little more electronegative, and they're pulled towards that way. Hydrogen and fluorine, I know it's kind of covered. I hope you can see it. Let me scroll up a smidge. There we go. Now it's still covered, excellent. Hydrogen and fluorine. Fluorine is 4.0, hydrogen is 2.1. Big difference between the electronegativity of those. As a result, fluorine is partially negative, hydrogen is partially positive. And this falls very much like in the gray area. It's kind of one of those bonds that falls between the cracks, so to speak. The difference is extremely close to 2, but it's not quite 2. All right? This is very unevenly shared. These shared electrons between hydrogen and fluorine are pulled way towards the fluorine side. These partial charges would be pretty large. They're approaching a value of 1. They're getting close to a value of 1. But it's not more than 2. We would still call this a covalent bond, but it's a polar covalent bond because we have these differences in charges. All right, that was very long-winded, but I hope I'm making sense today. All right, let's do some problems. And we'll call it a day. We got 4 problems here to look at. So, rank the elements from least electronegative to most electronegative. Now, I could give you these values, but what I'd like you to do is just use the general trend. Okay? The general trend is that from left to right across a row, electronegativity goes up. And then from bottom to top on a column, electronegativity goes up. So, grab your periodic table and try these. Pause the video, come on back, and we'll see if you can use the trend to correctly organize these elements. I'll be right back. All right, so in the first one, we have carbon, nitrogen, and oxygen. They are in the exact same row on the periodic table. They're in row 2. And again, if our trend is left to right, I'm going to rank this as carbon has the least, and then nitrogen, and then oxygen. Just left to right. Now, we did this weird thing with trend, right? When we looked at ionization energy, there was a spot where the trend kind of broke down, so to speak, or it was counterintuitive to what we would have expected. That might happen in some places with electronegativity, but I'm going to avoid those completely. All right? If an element is to the right of another on the same row, it's more electronegative. Don't overthink it. All right, the next one, we have sulfur and selenium and chlorine. All right, now, this one's a little funky because I'm making you go up and over. We are moving a column and we're moving a row. I'm making you do both. But here's the thing to remember. The one furthest down and left is the least. The one furthest up and right is the most. So, selenium is further down and to the left than the other two. Selenium is going to have the least. Sulfur is going to be the next. And then chlorine will be the most, all right? It's just kind of a matter of understanding that elements up and right are more electronegative, elements down and left are less electronegative. All right, last one. Titanium, sulfur, and germanium. Let's see, where's my titanium? There it is. No, that's not it. Where'd you go? There it is. Element 22. Element 22, element 16, and element 32. Same kind of thinking, right? Which one of those is furthest down and left? Titanium. Which one of those is next in that sequence? Looks like germanium. And which one is furthest up and to the right? Sulfur. Okay? Now, use the trend. Okay? Use the trend when we're looking at these rankings. How can we figure out which one's more electronegative? It's going to be based on how far up and to the right it is on the periodic table. All right, let's try problem number 2. But before we do, it's going to be extremely helpful for you to open up a document that I have posted on It's Learning. Okay, I apologize for not being able to print this off for you when I dropped off your packets, but you're probably going to want this because it'll help and make life so much easier. So let me go to this. This is what's known as an electronegativity periodic table. It looks just like the normal periodic table, but we have these red values in all of these boxes. We want to use this when we try the next problem. It's going to help immensely, okay? So please, if you have this, or if you can go to It's Learning and open this up, it'll help you a ton. Now, let's look at this. I want to rank all of these bonds from least polar to most polar. Well, least polar means the smallest difference in electronegativity. Most polar means the biggest difference in electronegativity. So let's look. In this first problem, I have fluorine bonded with carbon, silicon, and arsenic. Let's look up carbon, silicon, and arsenic on the periodic table. Oh, come on. There we go. So here's fluorine, it's 4.0. Carbon is 2.5. Silicon is 1.8. Arsenic is 2.0. What's the difference, right? 2.5 to 4 is the smallest. 2.0 to 4 is the next. 1.8 to 4 is last, or the largest. That's how we're going to rank these. The biggest difference in electronegativity means the most polar. So let's go back and rank these accordingly. I said that carbon fluorine is the least, okay? And I'm gonna be a little lazy and make this easier because I don't want to rewrite all this stuff. That's kind of tough. So least polar is going to be 1, most polar is going to be 3. All right, and we're going to go 1, 2, 3. So the least polar is the smallest difference. Arsenic would have been next because this was 2.0, that was 4.0. And silicon and fluorine would be the most because that was 1.8 and 4.0. Okay, you see what I'm saying? Try the next 3, pause the video, use that periodic table with those electronegativity values. The biggest difference is the most polar. The smallest difference is the least polar. That's all we're looking for. All right, so assuming you've tried the other 3, I hope you've tried the other 3, and if you still haven't, pause it and try them. Let's look at the next problem. The next problem we have phosphorus, chlorine, sulfur chlorine, silicon chlorine. So it's all chlorine, chlorine, chlorine. Let's look at the other 3 elements more closely. All right, so we have chlorine is 3.0. We have silicon, phosphorus, and sulfur. Sulfur chlorine is a difference of 0.5. Phosphorus chlorine is a difference of 0.9. Silicon chlorine is a difference of 1.2. That's our rank. It's going to go just based off of the trend left to right. Nice and easy. So sulfur is the closest. This is going to be the least polar, the smallest difference. Phosphorus was next. Silicon was last. Okay? Biggest difference is the most polar. Next, we have sulfur and fluorine, sulfur and chlorine, sulfur and boron. Let's go to the periodic table and figure it out. So we have, I can't even remember what the heck I said. Hey, sulfur and fluorine, sulfur and chlorine, sulfur and boron. All right. So sulfur and fluorine, difference of 1.5. Sulfur and chlorine, difference of 0.5. Sulfur and boron, difference of 0.5. Oh, so we have the same. Sulfur and chlorine is 0.5. Sulfur and boron is 0.5. So they're actually tied. Most polar is sulfur and fluorine, but the other 2 are equally polar. That's good to know. All right, so this is the most. We'll call that 3. I've been labeling 3 as the most polar. That's the biggest difference. But these 2 are actually the same, right? So I don't know how I want to do that. I don't know. These are the same. Okay, 1 and 2, they're tied. Tied for first, however you want to say it. They have the exact same difference, which means they have the exact same polarity. In other words, they are equally, the partial charges would be the exact same on both those molecules. All right, last series, titanium and chlorine, silicon and chlorine, chromium and chlorine. Let's go to the periodic table. All right, titanium and chlorine, difference of 1.5. Here's titanium, here's chlorine. Chromium and chlorine, difference of 1.4. Here and here. And my last element was chromium, silicon and chlorine. Let's try that. Silicon and chlorine, difference of 1.2. So this is going to follow the nice trend on the periodic table. 1.5, 3 and 1.5 is a difference of 1.5. 1.6 and 3 is a difference of 1.4. 1.8 and 3 is a difference of 1.2. So the least polar is silicon and chlorine. Next would be chromium and chlorine. And the largest difference would be the titanium and chlorine. Okay? Let's go to the next problem. Similar stuff, different style. Right partial charges. Now, you can use that periodic table if you want and look at the numbers. But we might not have to in some of these examples. Okay? If you see any of the FONCLBR, phone Chloe, bro, if you see any of those 5 elements, that's the 5 most electronegative elements. If it's not paired with another one of those, you can safely assume that that element is more electronegative. For example, carbon versus oxygen in the first problem. Oxygen is a member of the 5 most electronegative ones on the periodic table. FON, ClBr. It's the O. This is more electronegative, and that would be partially negatively charged. In the next one, phosphorus and hydrogen. This is way more abstract. Let's go to the periodic table. I have hydrogen way up top, 2.1. Phosphorus way over here, 2.1. Uh-oh, they're the exact same. If they're the exact same, it doesn't have partial charges. This is a different type of bond. This is called nonpolar covalent. There's no partial charges to write in, so B is done. Pretty easy. C, hydrogen and chlorine. Let's go back. Hydrogen, 2.1. Chlorine, 3.0. Okay, chlorine's more electronegative. It's going to get the partial negative charge. But did I need to go over there and look at those numbers? No, not at all, because chlorine is one of the 5 most. It's part of that group. So just looking at this and recognizing, oh, that's Chloe, right? Phone Chloe, bro. FONClBr. Okay, this is the more electronegative one. This is the less electronegative one. Partial negative, partial positive. Sorry, my delta for the negative is ugly, but oh well. D, bro. There's bro. It's bromine. That's an electronegative element too. Very electronegative. So this is going to be partially negative. This is going to be partially positive. All right, we've made it. We're at the end. We're close. Metallic bonds. Metals. It's the last chunk of this topic. Let's talk about metallic bonds really, really quickly. Covalent and ionic bonds are things you're familiar with, okay? Covalent bonds are when electrons are shared. Now, today we've learned that those electrons could be shared equally, and if they're shared perfectly equally, that's called nonpolar covalent. If they're shared unequally, that's called polar covalent. And then we have ionic bonds, which we know about as well. Last year we defined that as metal-nonmetal, and that definition still kind of works. But a better way of looking at it is using electronegativity. If the difference in electronegativity is bigger than 2, we would call that or classify that as ionic. But let's talk about one more type of bonding that is new. Good news, we don't have to know a ton about metallic bonding. But anyway, let's finish topic 2.1. So, metallic bonds are unique. When metallic elements form bonds with one another, the nuclei and core electrons of these atoms are packed in tightly together. Surrounding the tightly packed nuclei and core electrons are the valence electrons from all of these atoms. Metallic bonding is said to have a sea of electrons. Essentially, all of the valence electrons of all of these metallic atoms are free to move throughout this metal sample. Okay? So essentially, it kind of looks like this. Okay? Over in this example, I have positively charged nuclei and core electrons. These positive purple spheres are the nuclei of a metal. These metal atoms and nuclei are just kind of packed in tightly. All these positively charged nuclei are next to each other. And then you see this pink kind of blur, and there's a whole bunch of E1 minus written on there. Okay? The E1 minus are electrons, and the pink blur is representing the fact that all of these valence electrons are just free to kind of move and flow throughout the entirety of the system. Okay? This is another example of the same thing. It's just instead of a 1 plus metal, it's a 2 plus metal. This is like magnesium or something, right? So magnesium has 2 positive charge if it were to be an ion. And if it were to be pure metal magnesium, you would have all of these nuclei and core electrons. Again, these spheres are just kind of packed in tightly. And we have this cloud or this sea of electrons. These electrons and this pink blur is representing all of these valence electrons that can just free flow throughout the entirety of that sample. Okay? So you can visualize this. Yeah, we already talked about that. Sorry. 4. Why are metals such good conductors of electricity? Well, because there's endless valence electrons that can flow. Okay? Metals conduct electricity extremely well because the valence electrons are they're free to move. They're not confined. They're not stuck. Okay? Metals conduct electricity because of metallic bonding. Metallic bonding is this. Metallic bonding occurs when all of these positively charged nuclei of the metals just kind of pack in nice and tight, all in these layers and in this three-dimensional shape. But the valence electron of all of those atoms are free to move. And that free flow of the valence electrons is how electricity can travel through or be conducted through all of these metal samples. All right, long class today. I apologize. That's all I got. Please have a lovely day. Check your Infinite Campus. If something looks incorrect, give me an email and I'll fix it. Yeah, we'll catch you guys tomorrow. See ya.